Hey everybody, welcome back. This is our last section for Calculus 3. This is College of the Sequoias and it's fall of 2022. This is Anton's 11th edition and we're talking about Stokes' theorem today. We've seen a very specific form of Stokes' theorem before in Green's theorem. So let's see how we can generalize Green's theorem and get Stokes' theorem. We're going to start off. S is going to be a piecewise smooth oriented surface. It's bounded by a simple closed piecewise smooth curve C with positive orientation. We're going around the curve. So the boundary of the curve is going to be related to the surface interval, just like in Green's theorem. We've got a vector field F with components F, G, and H that have continuous first order partial differentials. And of course, they are continuous themselves. T, the vector T is of course the unit tangent vector to C. So the line integral of f dot dr is the same as f dot t ds. And this is going to be the curl of f dotted with n ds. Now, if I were to put that in words, it's the line integral around the boundary of the surface. So we got a surface, and we're going around the boundary of the surface. And at each point, we're doing the tangential component of the force. So tangential, the tangential component of the force around the boundary is going to equal the surface integral of the normal component of the curl of the force. Okay. And what we're doing effectively is if the integral is difficult in one dimension, but it's easier in two dimensions, we can upgrade by adding an integral and then adding a derivative. And vice versa. We can go the other way if we don't. Generally, we don't go the other way on this one, but we could. The proof of this is beyond the scope of this class, so we're just going to focus on the applications. There's a little more I want to say on this first, though. Let's see how this equals Green's theorem. If our n hat, our normal vector is 0, 0, 1, which is k. We're looking at the xy plane, and then the curl of f dotted with n is the curl of f dotted with k. And when you work that out, you get dg dx minus df dy, which is Green's theorem. So that's how this simplifies down to Green's theorem. So Green's theorem was working in the xy plane. Now we are not trapped in just the xy plane. Stokes' theorem allows us to do this at any weird angle. We can have a surface hanging in the air and do the line integral around that. Something that's worth noting, C does have to be the closed boundary about the surface, but the surface hasn't been specified. So if we're going from the line integral up to the surface, as long as the surface has the boundary of the curve, we can use any surface. So use the simplest one to integrate. I mean, we could have crazy looking ones like S3, S1, and S2 as being a nice little dome, maybe, or S1 being a dome. S2 is a wavy line. We could pick the one that has the easiest one to integrate. And sometimes just doing the actual plane that it's in is the easiest one to integrate, if you can get it into a plane that you recognize. Okay. And it's kind of like picturing blowing bubbles. You got this is the bubble wand. And before you blow a bubble in it, there's a bunch of soapy buildup on the thing. And so there's a lot of stuff there. When you blow air into it, that soap doesn't go anywhere except outward and make the bubble. There's no more soap there. There's no less soap there. It's just now in a different shape. That's the kind of idea that we're having here, where the shape doesn't matter. It's all the same amount of soap, no matter what shape we use. So use the simplest one you can. And if you can get it down to just the simple disk or simple shape it is in one dimension, or, a simple shape, do that. Let's take a look at some examples in our next video. Peace.